Hello, and welcome to the second in a series of videos about calculus limits. In the first video, I tried to introduce the idea of limits and talk about what they are, and I said that the limit as x approaches some number c of some function f of x equals some number L means that when x is close to c, then the values of f of x are all close to that number L. And in that previous video, I talked about how you could investigate limits graphically and numerically. Graphically, you can look at a graph of the function and see what it looks like the y-coordinate is or should be for a point on the graph whose x-coordinate is c. And numerically, you could evaluate the function when x is a number close to c. So if you plug in several numbers that are close to the number that x is approaching, and you get values that are all close to some particular value, that's a good indication that that value is the limit of that function. And I said in that previous video that those would give you evidence, but not proof of what a limit is. So in this video, we're going to talk about how to find for sure what the limit of some particular function is as x approaches some particular number. We're going to take an analytic approach to finding limits. And we're going to do this by using some theorems or limit laws. These can all be proved rigorously, mathematically, from the definition of a limit. And I'm not going to do that in this video. I may talk a little bit about how that works in another video, but we're just going to assume that these theorems can be proved, and if you want to see the proof of them, you can find them in a calculus textbook or something like that. So, first few theorems. The limit as x approaches c of a constant function b is just that constant. So for example, the limit as x approaches 5 of 17 would just be 17. No matter how close x gets to 5, 17 is just going to sit there being 17. The limit as x approaches c of x is c. So for example, the limit as x approaches 5 of x is 5. And that makes sense. When x is close to 5, then x is close to 5. And the limit as x approaches c of x to the n power is c to the n power. So, for example, the limit as x approaches 5 of x squared would be 5 squared, 25. Now, these are pretty obvious. They should make sense to you, but they and all the other theorems that I'm going to be showing you in this video can be proved rigorously from the definition of a limit. In this video, we're going to just accept that they can be proved or have been proved and be able to use them. Next, the limit of a constant times a function is equal to the constant times the limit of the function. So if you know the limit as x approaches c of f of x, and you look at a new function that's that original function times some constant b, the limit of that new function is just that number b times whatever the limit of the original function was. The limit of a sum is the sum of the limit. So the limit as x approaches any particular number of something plus something else is equal to the limit of the first thing plus the limit of the second thing, provided both of those limits exist. And same thing with subtraction. The limit of something minus something else is equal to the limit of the first thing minus the limit of the second thing, provided that both of those limits exist. Same thing with multiplication. The limit of f times g is the limit of f times the limit of g. And with division, the limit of f divided by g is equal to the limit of f divided by the limit of g, provided those limits exist and provided the limit of the denominator is not 0. And the limit as x approaches c of f of x to the nth power is equal to the limit of f of x to the nth power. So the limit of something to a power is you take the limit of the something and then raise that to that power. So for an example of these limit laws in action, suppose we want the limit as x approaches 2 of x squared minus 3x plus 5. What happens to that function as x gets close to 2? Well, we know that the limit of a difference is the difference of the limits, and the limit of a sum is the sum of the limits. And so we can break this up into the limit of x squared minus the limit of 3x plus the limit of 5, all as x approaches 2. And for the limit of 3x, we can use that rule about the limit of a constant times a function being equal to the constant times the limit of the function, and write that as 3 times the limit of x. And now we can use those first 3 facts that we saw. As x approaches 2, the limit of x squared would be 2 squared. The limit of x would be 2. And the limit of the constant 5 would just be 5. So putting those together, we have 2 squared minus 3 times 2 plus 5, which would be 4 minus 6 plus 5, which would be 3. Now at this point, you may be thinking, that looks like taking something that should be simple and making it way more complicated. So for something like this, what happens when x gets close to 2 isn't really any different than what happens when x is 2. And we could just plug in 2, evaluate the function, and what we get would just be 3. So for something like this, treating everything in terms of limits and justifying things using those limit laws, yeah, it really is kind of overkill. And that's because with a function like this, it behaves just like you would expect it to behave. There's nothing to really watch out for. It's an example of what we call a continuous function, a function that does exactly what it would be expected to do. And what happens when x is close to 2 exactly already matches up with what happens when x is 2. And if all functions were like this, then yeah, there wouldn't be any point to dealing with limits. But later on, we will see some more interesting cases where the limit is not just what happens when you plug in the number. But this was an example of a polynomial function. And we can take it as a theorem that if you have a polynomial function, the limit as x approaches any particular number of that polynomial function is just the same as the value you get when you plug in that number. The limit of p of x as x approaches c is just p of c. In other words, polynomial functions are continuous. I'm not going to talk much more about what continuous means in this video, but it kind of deserves a video all to itself. Also, if you've got a rational function, something that's in the form of a ratio of one polynomial over another, then the limit of that is just what you get if you plug in the number that x is approaching, provided that doesn't give you a 0 in the denominator. Now we will see that if you do get a 0 in the denominator, then you got to look at what happens to the numerator. And if you also get a 0 in the numerator, then the limit of the whole thing might or might not exist. But if the denominator gives you a 0 and the numerator gives you something other than 0, in that case, the limit of the whole rational function cannot exist. So that's coming up later in this video. But first, an example of a polynomial function. What's the limit as x approaches 10 of x cubed minus 5x squared plus 7x plus 8? Well, since that is a polynomial, we could just plug in the 10. Evaluate that function when x is 10, and that'll be the same as the limit as x approaches 10. So the closer x gets to 10, the closer x cubed gets to 10 cubed, and the closer x squared gets to 10 squared, and so on. So the whole thing is approaching 10 cubed minus 5 times 10 squared plus 7 times 10 plus 8, which is 1,000 minus 500 plus 70 plus 8, which is 578. And here's an example of a rational function. What's the limit as x approaches negative 2 of x squared plus 3x plus 7 over x squared minus 9? Well, if you evaluate that when x is negative 2, on top you get negative 2 squared plus 3 times negative 2 plus 7. And on the bottom you get negative 2 squared minus 9. So on top, 4 minus 6 plus 7 is negative 2 plus 7, that's 5. On the bottom, 4 minus 9 is negative 5. And 5 over negative 5 is negative 1. So that's what that limit is. And a couple more theorems. The limit as x approaches c of the nth root of x is the nth root of c. And for composite functions, if you've got a composite function f of g of x, if you know the limit of g of x, then the limit of f of g of x is just f of the limit of g of x. So again, this is the kind of thing that you would expect to be true, and in fact it is true. So for example, the limit as x approaches 2 of x squared minus 3 to the 10th power would be the limit as x approaches 2 of x squared minus 3, and then you take that limit and raise it to the 10th power. Well, as x approaches 2, x squared minus 3 would be approaching 2 squared minus 3. 4 minus 3 is 1, and so 1 to the 10th power is 1. Another example, what's the limit as x approaches 1 of the square root of 2x cubed minus 7x plus 41? Well, the 2x cubed minus 7x plus 41 would be approaching a limit of 2 times 1 cubed minus 7 times 1 plus 41, which is 36. And so the square root of that has a limit of square root of 36, which is 6. And the transcendental functions, things like trigonometric functions and exponential and logarithmic functions, have limits that, again, do pretty much what you would expect them to do. So if the number that x is approaching is something that is in the domain of the function we're looking at, then the limit as x approaches c of sine of x is sine of c. The limit of cosine x is cosine c. The limit of tangent x is tangent c. Same thing with cotangent and secant and cosecant. They're all continuous wherever they're defined. So that rules out things where the function is undefined. Like, for example, the tangent of pi over 2 is undefined. So if x were approaching pi over 2, the tangent of x would not have a limit. The limit as x approaches c of a to the x equals a to the c. So this is about exponential functions, and probably the most famous exponential function is e to the x. So the limit of e to the x would be e to the c. And its inverse, the natural logarithm function, works like that. The limit as x approaches c of the ln of x equals the ln of c. So some examples of these facts. The limit as x approaches pi of the function cosine of x equals cosine of pi, which is negative 1. The limit as x approaches 7 of the natural logarithm of 5x minus 34. Well, as x approaches 7, 5x minus 34 would be approaching 5 times 7 minus 34, which is 35 minus 34, or 1. And so the natural logarithm of that would be approaching the natural logarithm of 1, which is 0. And the limit as x approaches pi of sine of x plus cosine of 2x over tangent of 3x plus 4x would be the sine of pi plus the cosine of 2 pi over the tangent of 3 pi plus 4 pi. And that would be 0 plus 1 on top over 0 plus 4 pi on the bottom, so 1 over 4 pi. Now, so far, all of these examples that we've been seeing of limits have been pretty straightforward, and what happens when you take the limit as x approaches a number has just been the same as what happens if you just plug in that number. But don't be deceived. Limits don't always work that way. So now things are going to get a little more interesting. So this theorem is the key to a lot of what's going on in the rest of this video. If you have two functions that agree at all but one point, that is, f of x and g of x give you the same value, not when x equals c, but for all the other x's that are not equal to c, at least close to c, in some open interval containing c. So maybe for all x, or maybe just for all x within some little interval around c. But for all x, at least within some open interval containing c, other than c itself. If the only difference between the functions is what happens right at that particular number c, then they have the same limit as x approaches c. Because remember, limits don't depend on what happens when x equals c, only on what happens when x is close to c. So as long as they agree about what happens when x is really, really close to c, it doesn't matter what happens when x equals c. And we saw an example of that in the previous video. So if you watched part 1, you saw my example of the function 2x squared minus 7x plus 3 over x minus 3. And you saw how that can be simplified to 2x minus 1 by factoring and then canceling the common factor of x minus 3. So the original function 2x squared minus 7x plus 3 over x minus 3 is equal to 2x minus 1 for all x other than 3. The only difference between those two functions is that the first one is undefined when x is 3, because you get a 0 in the denominator, and the second one is defined for all x. And since they're the same except for 3, they have the same limit. The limit of that original function is the same as the limit of 2x minus 1, which would be 2 times 3 minus 1, which would be 5. So here on out, the limits that we're going to be working with, the function itself might be undefined if you plug in the number that x is approaching, but that doesn't necessarily mean that the limit doesn't exist. So these limits are going to be a little more interesting, a little trickier. They're going to be a little like little puzzles to solve to try to figure out what the limit is. So, example, what's the limit as x approaches negative 3 of x squared plus 14x plus 33 over x squared minus 9? Notice that the numerator is approaching negative 3 squared plus 14 times negative 3 plus 33, which is 0. And the denominator is approaching negative 3 squared minus 9, which is 0. So here we have a situation where the numerator and the denominator are both approaching 0. And in a case like that, the function would be undefined right at negative 3, but the limit as x approaches negative 3 could still exist. And so to find out what's going on as x approaches negative 3, I'm going to factor. The numerator can be factored into x plus 11 times x plus 3. If you multiply that back together, you do get x squared plus 14x plus 33. And the denominator is a difference of two squares. It's x squared minus 3 squared, so it can be factored into x minus 3 times x plus 3. And since the numerator and the denominator have a common factor of x plus 3, we can divide that out and reduce this to just x plus 11 over x minus 3. So the only difference between the function we started with and x plus 11 over x minus 3 is what happens right at -3. The original function would have been undefined. It would have been a division by zero error. The function we simplified it to is not undefined. It works perfectly well when x is -3. But aside from that, for all other x's, they're equal, and so they have the same limit. So now we can see what happens as x approaches -3. The numerator would be going to -3 plus 11, that's 8. The denominator would be going to -3 minus 3, that's -6. And so the limit of the whole thing is 8 over -6, or -4/3. And here's a graph of the function that we started out with. If we draw the graph of x squared plus 14x plus 33 over x squared minus 9, it looks like there's a point on the graph with an x coordinate of -3, and the y coordinate of that point, well, you may be not able to see exactly from the graph, but it's -4/3, -1 1/3. And so graphically, the limit is what it looks like the y coordinate should be when the x coordinate is that number that we were talking about, x approaching. So this picture agrees with what we found analytically by analyzing the function, by factoring and canceling out the common factor, and then seeing what happens as x approaches -3. So in a situation like that, where you've got a fractional expression, the function you're looking for the limit of is made up of a numerator over a denominator, start by looking at the numerator and the denominator individually and see what they are doing. What are they approaching? If the denominator doesn't approach 0, if it approaches some other number, then you're good to go. You just take whatever the limit of the numerator is divided by whatever the limit of the denominator is. If the denominator approaches 0 and the numerator doesn't, that's enough to tell you that the limit of the whole thing cannot exist. So if you see the denominator going to 0 and the numerator doing something else other than approaching 0, you can conclude from that that the limit of the whole thing just does not exist. But if the denominator and the numerator both approach 0, the limit might exist, or it might not. So you still have some work to do to figure out what the limit is, or whether it actually does exist or not. So to figure that out, often what you can do is what we did in that last example. Try factoring and canceling the common factor. Sometimes you can do something else, some other sort of mathematical manipulation to simplify or transform the function. So like I said, limits like these are a little like little puzzles to solve, and we'll be seeing some more examples of that coming up, well, right now. What's the limit as t approaches -1 of t squared plus 2t plus 1 over t squared plus 3t plus 2? Well, what happens as x approaches -1? What's happening to the numerator, and what's happening to the denominator? The numerator is approaching -1 squared plus 2 times -1 plus 1, that's 0. The denominator is approaching -1 squared plus 3 times -1 plus 2, and that works out to be 0. So we have one of these 0 over 0 situations. And that means we can factor the numerator and the denominator. The numerator factors into t plus 1 times another t plus 1, or you could have written that as t plus 1 squared. And the denominator factors into t plus 1 times t plus 2. But they both have a factor of t plus 1 that we can cancel out. And now look what happens as t approaches -1. Now we have a numerator that's approaching 0 over a denominator that's approaching 1. And now that the denominator no longer approaches 0, we have our limit. The limit is 0 divided by 1, which is 0. So when t is close to -1, t squared plus 2t plus 1 over t squared plus 3t plus 2 is close to 0. Next example, what's the limit as x approaches 4 of x squared plus x minus 20 over x minus 4? Now, just a little reminder, you're watching this on a video. You can pause the video. if you want to try and figure this out for yourself before I show you how. So if you think you've got the hang of this and want to try to get ahead of me, you are welcome to pause the video and try to figure it out yourself first. So what happens as x approaches 4? The numerator approaches 0, 4 squared plus 4 minus 20. The denominator approaches 0, 4 minus 4. So we have one of these 0 over 0 situations. The numerator can be factored. One of the factors is x minus 4. That's what's making it go to 0. If a polynomial approaches 0 as x approaches some particular number, that tells you that x minus that number is going to be one of the factors that it factors into. So that gives you a hint as to how to factor it. Well, it factors into x minus 4 times x plus 5. So now we can divide out the x minus 4s. And now look what happens as x approaches 4. The limit of x plus 5 is 4 plus 5, which is 9. So we have our limit. What about this one? The limit as x approaches 0 of 3x to the 9th minus x to the 5th over x to the 7th minus 2x to the 6th plus 3x to the 5th. So what happens to the numerator and what happens to the denominator as x approaches 0? Well, they are both approaching 0, since each individual term involves x to some power. But on top, we can factor out, well, the greatest common factor up there would be x to the 5th power. And on the bottom, the greatest common factor there would also be x to the 5th power. So we can factor those out and then divide out that common factor of x to the 5th. And now look what happens as x approaches 0. Now on top, we get 0 minus 1, or just negative 1. On the bottom, we get 0 minus 0 plus 3, or just 3. And so the limit is negative 1 over 3. That is negative 1/3. What about this one? The limit as x approaches 0 of x cubed minus 7x squared plus 11x all over x. So we have a numerator and a denominator that individually both approach 0. In the numerator, we can factor out a common factor of x and then divide that out with the x in the denominator. And now we're looking at the limit as x approaches 0 of x squared minus 7x plus 11. And that limit would be 0 minus 0 plus 11, which is 11. How about the limit as x approaches 3 of x squared plus 3x plus 7 over x squared minus 9? Well, what happens as x approaches 3? The numerator approaches 3 squared plus 3 times 3 plus 7, which is 25. The denominator approaches 3 squared minus 9, which is 0. And so here we have a situation where the denominator goes to 0, but the numerator does not. It goes to 25. And so the limit does not exist. Remember I said if the denominator goes to 0 and the numerator doesn't, that's enough to let you conclude that the limit of the whole thing just does not exist. And if you look at the graph, you can maybe see why. Here's the graph of x squared plus 3x plus 7 over x squared minus 9, and look at what happens when x is close to 3. It doesn't look like there's a point on the graph with an x coordinate of 3. And if I asked you to put a point where it should go, there isn't really a place to put a point. Because for some of the x's on the graph that are close to 3, like a little bit bigger than 3, we've got y coordinates that are way the heck up here. And then if x is a little bit less than 3, the y coordinates are way down here. But there's no single number that the y coordinates are always close to whenever x is close to 3. So the limit just does not exist. So whenever the denominator approaches 0 while the numerator does not approach 0, you can conclude from that that the limit does not exist. Next example, 2 minus the square root of x plus 1 over x minus 3. So what happens as x approaches 3? The numerator approaches 2 minus the square root of 4. That is 2 minus 2, which is 0. and the denominator approaches 3 minus 3, which is 0. So we have another one of these 0 over 0 kinds of situations. Now, the numerator is not a polynomial, so we can't really factor it, but we can try a different trick. What I'm going to do here is I'm going to multiply the numerator and the denominator of this expression both by the same quantity, 2 plus the square root of x plus 1. Because when you multiply something minus something by that same something plus that same other something, you get the first thing squared minus the second thing squared. So two binomials that are the same except that one has a minus and one has a plus, when you multiply them together, you just get the first thing squared minus the second thing squared. So that's what I did here. I multiplied 2 minus the square root of x plus 1 by 2 plus the square root of x plus 1. And that way I get 2 squared, which is 4, minus the square root of x plus 1 squared, which is just x plus 1. So that 4 minus that x plus 1, well, the 4 minus the 1 is 3, and then you got that minus the x. So 3 minus x on top over x minus 3 times 2 plus the square root of x plus 1 on the bottom. And I could multiply that out, but I don't want to. Instead, I want to cancel. Now on top we have 3 minus x, and on the bottom we have x minus 3, and they're not quite the same thing since the subtraction is in the opposite order. But they are opposites of one another. 3 minus x would be like negative 1 times x minus 3. So I can cancel those, and I'm left with a factor of negative 1. And now, if I let x approach 3, the numerator is just negative 1. The denominator approaches 2 plus the square root of 3 plus 1, that is 2 plus the square root of 4, or 2 plus 2. And so the limit is, sorry, that should be a negative 1/4. Now, what about this one? The limit as x approaches 0 of the sine of 1 over x. Now, this limit does not exist, but it's a little bit tricky to see why it doesn't exist. It's not just because it's undefined when x is 0. Because remember, for limits, we don't care what happens when x equals that number, just what happens when x is close to or approaching that number. And we could say that the limit of 1 over x doesn't exist because its denominator is going to 0, but that doesn't necessarily mean that the sine of 1 over x has a limit that doesn't exist. So what's really going on here? Well, look at the graph. Here's what the graph of that function looks like. And if x is close to 0, that means you're talking about a little tiny number for x, like 1/1000th. And then 1 over x would be 1 over 1/1000th, which would be 1,000. So if you look at numbers that are really close to 0, and then you take their reciprocals 1 over those numbers, you get numbers that are really big. But the sine of a really big number, you never know what's going to happen. Depends on what number it is. Sometimes the sign is positive 1, sometimes the sign is negative 1, sometimes the sign is somewhere in between. So no matter how close x gets to 0, there are always going to be values for 1 over x whose sign is positive 1, and there are going to be others whose sign is negative 1, and others whose sign is 0, and others whose sign is 1/2, and so on. So there isn't just one particular number that sine of 1 over x is always close to whenever x is close to 0. That means there isn't a limit, because a limit would have to be a one particular number that function is always close to whenever x is close to 0. So that's why that limit doesn't exist. But compare that with the limit as x approaches 0 of x times the sine of 1 over x. The sine of 1 over x is still doing all sorts of weird things, but we're multiplying that by x. And of course, if x is close to 0, then x is close to 0. And if we take that x that's close to 0 and multiply it by the sine of 1 over x, well, the sine of 1 over x might be 1, but x times 1 would just be x. It might be negative 1, but x times negative 1 would be negative x. It might be somewhere in between. So x times the sine of 1 over x is always going to be somewhere in between x times 1 and x times negative 1, but those are both getting close to 0. And so x times something between negative 1 and 1 is going to be, if anything, even closer to 0. So that limit will be 0, because that kind of gets squeezed into 0 in between those other two things, just plain 1x and just plain negative 1x, that are also approaching 0. And this is a kind of situation that is dealt with by something that is called the squeeze theorem. So basically, the idea is that if your function is stuck between two other functions that both approach the same limit, your function must also approach that same limit. So a more formal statement of the theorem goes like this. Suppose g of x and h of x are functions such that the limit as x approaches c of g of x is equal to the limit as x approaches c of h of x. They have the same limit as each other, and we'll call that limit L. And suppose f of x is a function that's in between them. So g of x is less than or equal to f of x is less than or equal to h of x. So f of x always has a value that's somewhere greater than or equal to one of the functions, but less than or equal to the other one for all x in some open interval containing c, except possibly at c itself. So that happens for all the x's that are close to, but not necessarily equal to, the number that x is approaching. In that case, the limit as x approaches c of f of x is L. That is, it's the same limit as the limit of g and h. And this is useful, well, in a few theoretical situations. It gets used in proving a couple other theorems, but it's also useful in situations where you have something times the sine of something, or something times the cosine of something, because you can take advantage of the fact that sine of anything and cosine of anything always give you a value that's somewhere between -1 and 1. So all the really good examples I know of that involve the squeeze theorem are pretty much set up like that. So here's an example. Suppose we want the limit as x approaches 0 of x squared times the cosine of x squared plus 3 over x squared minus 2x. Now, my first instinct is to see what's happening with this. As x goes to 0, x squared plus 3 goes to 3, and x squared minus 2x goes to 0. And we have a situation where we got a 3 on top and a 0 on the bottom. And if we were just looking at the limit of just that, it wouldn't exist. But that's not what we're looking at. We're not just looking at the limit of that part. We're looking at the limit of the cosine of that thing times x squared. So it doesn't matter that that's undefined when x equals 0, and it doesn't really matter what happens to it when x is close to 0. The cosine of that thing is going to be between -1 and 1, because the cosine of anything is always between -1 and 1. And so the cosine of anything times x squared is going to be between -1 times x squared and +1 times x squared. So our function here, the function that we want the limit of, is stuck in between two other functions that are a lot simpler. The function -x squared and the function +x squared. And they both have a limit of 0. The limit as x approaches 0 of -x squared is 0. And the limit as x approaches 0 of +x squared is 0. And so, by the squeeze theorem, the limit as x approaches 0 of x squared times the cosine of x squared plus 3 over x squared minus 2x is 0. Here's the picture. The red parabola is the graph of the function -x squared, and it's got a limit of 0. As x approaches 0, -x squared approaches 0. And the green parabola is +x squared, and it's also got a limit of 0. And the blue curve that's doing all sorts of weird things, but always staying between the red and green parabolas is x squared times the cosine of x squared plus 3 over x squared minus 2x. So it does all sorts of weird things, but it's squeezed in between those other two functions that are both approaching 0, so it has nowhere to go but to 0 as well. The walls are closing in, you can't escape, you've got to approach 0. Next theorem, the limit as x approaches 0 of the sine of x over x is 1. Now, if you looked at my previous video, I showed you how this makes sense graphically and numerically. I showed you if you plug in some values of x that are close to 0, you get values that are very close to 1. And it can be proved that the limit as x approaches 0 of the function sine of x over x is in fact 1. I'm not going to show you the proof. It gets a little complicated. It involves facts from geometry and trigonometry, and it does use that squeeze theorem, and it assumes that when you're talking about sine of x, the x refers to radians. And if you want to see that proof, you can probably find it in just about any calculus textbook, and I'm sure there's places online that you can find it. So we can now, henceforth, assume that it's true that as x approaches 0, the limit of sine x over x is 1. And we can use that fact to find other related limits. Like, for example, the limit as x approaches 0 of the sine of x over 3x. That's almost the same as sine x over x. It's just got an extra 3 down there. But we can think of that as, well, notice that the numerator and denominator both approach 0. But we can think of it as a 1 over 3 times a sine of x over x. So it's just a constant times something that we know the limit of. And so the limit of a constant times a function is the constant times the limit of the function. And we just saw the limit as x approaches 0 of sine x over x is 1. So this limit should be 1/3 times 1. That is 1/3. How about the limit as x approaches 0 of sine x over 2x squared plus x? With a numerator and a denominator that are both approaching 0. So that doesn't really tell us anything one way or the other. It just tells us the limit might exist, but we need to do some further work to figure out exactly what it is. And what I'm going to do is factor out a common factor of x on the bottom, and then pull out sine x over x times 1 over that other factor, 2x plus 1. And now use the fact that the limit of a product is the product of the limits. Break it up into the limit of sine x over x times the limit of 1 over 2x plus 1. We know that the limit of sine x over x is 1. And then as x approaches 0, 1 over 2x plus 1 would be approaching 1 over 0 plus 1. That is 1. And so the limit of the whole thing is 1 times 1, which is 1. How about the limit as x approaches 0 of tangent of x over x? Well, as x approaches 0, the tangent of x is approaching the tangent of 0, which is 0. And the x itself is, of course, approaching 0. And what can we do with this? If that were a sine instead of a tangent, we would know what the limit is. Is there a relationship between tangent and sine? Why, yes, there is. I remember from trigonometry that the tangent of x is equivalent to the sine of x over the cosine of x. So I could just write it like that. And then I can break that up into the sine of x times 1 over the cosine of x. So we have the sine of x over x times 1 over the cosine of x. And both of those have limits that we know what to do with. We know the limit as x approaches 0 of sine of x over x is 1. And since the cosine of 0 is 1, the limit as x approaches 0, 1 over the cosine of x is 1 over 1, which is 1. And so the limit of the whole thing would be 1 times 1, which is 1. How about the limit as x approaches pi of sine of x over 5x? Careful! Now, here's where I've seen people get careless and make mistakes and think, oh, sine x over x, that's 1. Just pull out the 1/5 and it's 1/5 times 1. And wait a minute, that only applies when x is approaching 0. We saw that the limit as x approaches 0 of sine x over x is 1. But here, x is not approaching 0. X is approaching pi. So what's happening now? Well, on top, the sine of x is approaching the sine of pi, which is 0. And on the bottom, 5x is approaching 5 times pi, which is not 0, it's 5 pi. And so the limit is 0 over 5 pi, which is 0. So be careful to only use this fact when x is approaching 0. Now what about the limit as x approaches 0 of the cosine of x minus 1 over x? And notice, by the way, that cosine of 0 would be 1, and so the limit of the numerator would be 1 minus 1, which is 0, and the denominator is also going to 0. So here I'm going to use a similar trick to what I've used before, and I'm going to multiply the numerator and the denominator by the conjugate of what we already have here. The same thing, but with a different sign, a plus instead of a minus. Because when I multiply these together, I'm going to get the first thing squared minus the second thing squared. So I multiplied top and bottom by cosine of x plus 1, and on top I got cosine of x squared minus 1 squared, which is still 1. And then I'm going to take advantage of a famous trigonometric identity that says that sine squared plus cosine squared is always equal to 1. So that would mean that the cosine squared minus 1 is equal to the sine squared of x. Actually, no, cosine squared minus 1 equals negative sine squared. And now that I'm looking at the limit as x approaches 0 of negative sine squared of x over x times cosine x plus 1, I can separate that out into, okay, we pull out a sine x on top and an x on the bottom, and then what's left is a negative sine x on top and a cosine x plus 1 on the bottom. So the sine x over x, the limit is 1. Negative sine x over cosine x plus 1, if you let x approach 0, the numerator approaches negative sine of 0, which is 0. The denominator approaches cosine of 0 plus 1, which is 1 plus 1, or 2. And so the limit of the whole thing is a 1 here times a 0 here, which is 0. So it turns out that the limit as x approaches 0 of the cosine of x minus 1 over x, that limit is 0. And some calculus textbooks present this as a theorem in its own right. So you can take this as a theorem, and if it ever comes up in solving some other limit problem, you can say, oh, we have the cosine as x the limit as x approaches 0 of cosine x minus 1 over x. I know what that limit is. It's 0. What about this example? What's the limit as x approaches 10 of cosine of x squared plus 5 over 10 minus x times the secant of x squared plus 5 over 10 minus x? Now think about this for a minute. At first you're tempted to say something like, oh, it's undefined, or there's no limit, or something like that because of the 0 in the denominator when x approaches 10. But we don't really care about that. Remember, we don't care what happens when x is 10. All we care about is what happens when x is close to 10. And as long as x is only close to 10, then x squared plus 5 over 10 minus x, well, whatever it is, it's something. And the cosine of that something times the secant of that very same something is always just going to be equal to 1. Because if you remember from trigonometry, the cosine function and the secant function are reciprocals of one another. So if we multiply them together, we're always going to get 1. And so this function here is the exact same thing as the constant function 1 for all x close to 10. And since they're the same function, they have the same limit, and that limit is 1. Okay, how about this example? What's the limit as x approaches 0 of 1 over x plus 7 minus 1/7 all over x? So the numerator is approaching 1 over 7 minus 1 over 7. That would be 0. The denominator, of course, is also approaching 0. So here's another one of those 0 over 0 situations. Can you think of anything we could do to rearrange or rewrite or simplify or transform this function into something different that's equivalent? Well, on top, we're subtracting two fractions. And to actually subtract fractions, you need to get a common denominator. And here we can get that common denominator by multiplying the first fraction by 7 on top and on the bottom, and multiplying the second fraction by x plus 7 on top and on the bottom. So now that they have the same denominator, 7 times x plus 7, we can combine them, and the numerators, 7 minus x plus 7. Well, the 7 minus the 7 is going to cancel out, and we're just going to have a minus x over 7 times x plus 7. So that's the big numerator of the big thing. The denominator of the big thing is still x, but the numerator and the denominator both have a factor of x that we can divide out and reduce it to negative 1 over 7 times x plus 7 over just 1. And now we can let x go ahead and go to 0. So this x here is going to 0. X plus 7 is going to 7. 7 times 7 is going to 49. Negative 1 over that is going to negative 1 over 49 over 1. We get a limit of negative 1/49. What is the limit as x approaches 2 of the natural log of x minus 1 squared over the natural log of x minus 1? Well, the numerator, as x approaches 2, x minus 1 is approaching 1, 1 squared would be 1, and the natural log of 1 would be 0. So we got a numerator that's approaching 0. And we've got a denominator that's also approaching the natural log of 1, which is 0. So another 0 over 0 kind of situation. We need some sort of trick to simplify or reduce or transform this function into one where we can see what's going on. And here we can take advantage of one of the properties of logarithms, the one that says that the logarithm of something to a power is always equal to the power times the logarithm of the something. So the ln of x minus 1 squared would be equivalent to 2 times the ln of x minus 1. Oh, so now we've got 2 times the ln of x minus 1 on top, and then we're dividing that by the ln of x minus 1. Well, the ln of x minus 1's divide out, reducing it to just 2 over 1 or 2, and so the limit of a constant is just that constant, 2. And this is going to be my last example for this video, but I'm going to do it more than one way. Here's an example of something that we can do several different ways, and you might even be able to think of some other way that I didn't think of. But we want the limit as x approaches 0 of secant of x minus 1 over tangent of x. Now, the secant of 0 would be 1. It would be the reciprocal of the cosine of 0, but that's also 1. And then 1 minus 1 would be 0. And the tangent of 0 would be 0. So we have a numerator and a denominator that are both individually approaching 0. So how can we solve this puzzle? What can we do to transform this into something where we don't just get a 0 on top and on the bottom? Well, one thing you can do when you have an expression involving other trigonometric functions like secant and tangent, you can always transform it into an expression that only involves sine and or cosine. In this case, we can take secant of x and write it as 1 over cosine of x, and we can take tangent of x and write it as sine of x over cosine of x. Now we can take the numerator and the denominator and multiply through by cosine of x, and it becomes 1 minus cosine x over sine x. Now we're not done yet. We still have a numerator and a denominator that both approach 0. But now, kind of looks a little more similar to what we've been dealing with before. I could pull out my old trick of multiplying the 1 minus cosine x by 1 plus cosine x. By the same thing, but with a plus instead of a minus, because then when I multiply that out, I get 1 squared minus cosine of x squared. And then using that Pythagorean trigonometric identity that says that sine squared plus cosine squared is always equal to 1, 1 minus cosine squared is equal to sine squared. Now, on top we've got a sine x times another sine x. On the bottom we've got a sine x times a 1 plus cosine x. We can divide out that factor of sine x that appears on top and on the bottom and reduce it to just sine x to the first power on top over 1 plus cosine x on the bottom. Now we can go ahead and let x approach 0 and see what happens on top and on the bottom. The numerator approaches the sine of 0, which is 0. The denominator approaches 1 plus the cosine of 0, which is 1 plus 1 or 2. And a 0 over a 2 equals 0. So we have our limit. The limit turned out to be 0. So that was one way of finding this limit. But there are other ways you could do it. Here's a second way that I thought of. It starts out the same as what we did before, get down to where it's equal to the limit as x approaches 0 of 1 minus cosine x over sine x. But this time what I'm going to do is take the numerator and the denominator and divide them both by x. So now we're looking at the limit as x approaches 0 of 1 minus cosine x over sine of x over x. And those both look kind of familiar. We know that the limit of sine of x over x as x approaches 0 is 1. And we saw earlier that the limit as x approaches 0 of cosine x minus 1 over x is 0. And this isn't quite the same as that because the subtraction's in the opposite order, but it is the opposite of that. It is negative 1 times cosine of x minus 1. So we can write it as negative cosine x minus 1 over x. And now we know what the limit of the numerator is. It's 0. We know what the limit of the denominator is. It's 1. And the limit of the whole thing would be 0 over 1, which is 0. And here is a third way that doesn't involve transforming into sines and cosines, but just leaving it in terms of secant and tangent. So the third way would be to multiply the numerator and the denominator both by secant of x plus 1. And here, if you multiply out the numerator, you get secant squared minus 1. But that's equivalent to tangent squared. That's another one of those basic Pythagorean trigonometric identities. Secant squared of x minus 1 is always just equal to tangent squared of x. Now we can divide the numerator and denominator each by that common factor of tangent of x, and it reduces to the limit as x approaches 0 of tangent of x over secant of x plus 1. Now as x approaches 0, the tangent of x approaches the tangent of 0, which is 0. And the secant of 0 would be 1, so the denominator approaches 1 plus 1, or 2. And so the whole thing has a limit of 0 over 2, which is 0. Okay, I hope you thought that was kind of fun. What we haven't talked about yet in this video or the one before it, there's still other things to talk about related to limits, like the official delta epsilon definition of a limit and how that works. One-sided limit, like as x approaches some number from the left or from the right. Infinite limits, where the limit doesn't exist, but you could be a bit more specific about how or why it doesn't exist by saying it's infinity or it's negative infinity. And you can talk about limits as x approaches infinity or as x approaches negative infinity. And then I did mention the concept of continuity or a function being continuous. So I said that kind of deserves its own video. So hopefully I'll be back with some more videos to discuss these other limit-related topics. See you then.